Good afternoon.
Good afternoon, ladies and gentlemen. I'm John.
I'm David.
And here we are on Q&A Wednesday. Team Talk Friday. I always get these wrong. I don't know, I just work around the clock. So what are we doing today? So Team Talk Tuesday, we're talking about one of the biggest problems in the concrete industry, corrosion of reinforcing steel. And I believe it was the Portland Cement Association that had an article by whoever, about how it's one of the leading causes for concrete infrastructure failure.
Yep, we design concrete with rebar. If the rebar isn't working, we get failure.
So we've got an awesome discussion. I'm going to go over the science of corrosion, both in saltwater baths as well as concrete. David, what are you going to be doing today?
I'm going to talk a little bit about when bad things start to happen, why does that affect the concrete?
And Whitney, what are you...
She'll be here.
Alright, somebody was late today. Okay, so...
Somebody's got to run the business.
Somebody's got to run the business. Okay, so I get to talk about the science of corrosion. And I've got my coach standing off to the side. Looky, looky, looky. This is a short glimpse into what corrosion is all about. And when you first look at it, I want you to imagine a piece of steel rebar in a salt water bath. So you got a lot of water, a little bit of steel, and we look at our steel surface, we can call it an abraded ion, or even abraded iron, or not iron, abraded iron. I was making fun of that before. But what that means is, on the surface of our reinforcing steel, we do have some free atoms that are ready to give up some electrons, as well as pop off that surface, especially if you have something like water and oxygen to accelerate that reaction. And that's ultimately what we see when we take our steel and put it in our salt water bath. Right at the surface, we're going to have that release or that disassociation of iron off of our steel with the positive 2 charge. We're still going to have 2 electrons within our anodic region that are going to contribute in our cathodic region to this development of hydroxides with those electrons, oxygen and water. And the jacked up thing is, once those hydroxides are available, again remember, we're trying to capture a singular event, and we never have a singular event. A corrosion doesn't happen once a second. We're actually seeing multiple events going on simultaneously at our surface, and ultimately it's this combination of hydroxide with iron, sorry about that, that creates our rust. Now, in a water bath, you have this dynamic movement. I think, what do they call it? I remember in 8th grade, it's dynamic
equilibrium.
Dynamic equilibrium. It never reaches dynamic equilibrium because you have so much salt water and rust interchanging, and it's really not until we get this brown, soupy, reddish goop that we've used up all the water and we've effectively changed the entire pH of that solution do we finally stop rusting, or we destroy our entire piece of rebar. Now in concrete, it changes. Because within concrete, good concrete, once that rust happens, that rust acts as a protective coating. And as long as we don't have the migration of electrons or pore water, that rust won't really continue. And that's the problem. That's the unfortunate reality. Especially when we have subpar concrete, if there's too much water, if there was cracking. But with too much water, we create those bleed channels that can go all the way down to our reinforcement. That allows the migration of water and salts that can exacerbate that steel corrosion. And as Whitney will tell you here in a little bit, we've got a major problem with steel corrosion here in the United States, and I believe it was in that Portland Cement Association manual that you read so long ago.
That's
and have
right.
all that information.
I know, it was a lot of information.
That's the science on steel corrosion. That's the good side of it with concrete, the bad side of it, the unfortunate reality. And David's going to jump in and talk about...
All right, so we designed reinforced concrete with reinforced steel. And as John said, bad things can happen. Why are they bad? Well, corrosion, when it starts to occur, it has an increase in volume. What is an increase in volume? It's tension. Is tension bad? Tension is bad. So concrete just doesn't like tension. Tension is bad. So if we get an increase in volume, that's tension, that's a bad thing. We design rebar by its area. If we get even a little bit of change in area, we may not have accounted for that in design. But worse than that is the bonding. If we get this rust surrounding our rebar, it breaks down the bond, and we need that bond so that when the concrete flexes, that rebar, that concrete holds on that rebar and says, I'm sorry, I've got hold of this. You can't go anywhere. Because as that corrosion occurs and that bond loosens up, we get that tension, and the concrete says, gosh, I don't have anything really to hold on to now. You know, I'm going to let go. I'm sorry, I'm going to fail. So, you know, our structures are sending us messages, and one of the messages is rebar's not doing what it's supposed to.
That was perfect.
Yeah, then listen.
So when you said the area increases, it's not the area of steel, it's area of the rust that increases. What happens to that steel?
Yeah, it's both bad news. The corrosion, the rust itself causes an increase in volume.
Right.
But by rusting, the actual usable area of the steel is less. So you have
Shrinking
less
down.
usable steel, that's bad. And we have rust, which is causing an increase in volume, that's bad.
And then the stresses occur from
That
Well, and then
increases
more
the
water
stresses.
can come in because it's opening up pockets, right? And then
Right.
that's just exacerbating the problem.
And that's where our problem is. We have a $48 billion a year concrete industry. $8.5 billion is put back into the concrete infrastructure system to deal with the maintenance associated with concrete degradation. Corrosion of reinforcing steel accounts for one of those primary mechanisms of premature concrete failure. Like, if it's not the number one thing we're trying to solve today, I think the ultimate question is, why is it not, and what the heck do we need to do to change our focus? We have articles about innovation of concrete 2030. Like, why the hell are we talking about, excuse my language, why are we talking about concrete 2030 when we've got concrete from 1986, which we're still using today, and we're still paying for it? Every year we use it, we pay for that concrete.
Right.
And we're still using the same technologies that we used, albeit with some innovations.
Some innovation. But the materials are, a lot of the materials that we used back then, we don't have that same quality of material anymore because we've used them up. We've used a lot of our natural resources, so we're running into more issues with the raw materials that we have, and a lot of people are incredibly hesitant to look at these innovations to try to solve a problem, and it's a problem that's getting worse.
Can I sidebar?
Please.
Sidebar. So we've been talking about reinforced concrete. We all know what that is. We take concrete, we take reinforcing bars. What about pre-stressed concrete? Pre-stressed concrete, we have these nice, very strong steel wires. We put them at very high tension, cast concrete around it, cut them loose. They put a compression on the concrete. Concrete loves compression, and so that works really well until we start to get corrosion. Because in pre-stressed concrete, we get a little pit of corrosion, and it calls stress intensity.
Oh my gosh.
So that
singularity.
that one little spot, all of a sudden, when it had this nice uniform stress on it, now it doesn't. Now it's got this one spot that's getting, that the area gets smaller, causes stress intensity, and when that piece of steel breaks, it sounds like a .22 rifle. It does. You can actually hear it. It goes ping when it breaks.
Wow.
You can actually hear it. And so in pre-stress and post-tension, the problem's even worse because that first little spot of corrosion calls that stress intensity.
That's structurally. Now, if you look at steel fibers, aesthetically, we use steel fibers to keep concrete pads together, especially in warehouse floors, agricultural floors. If we have a subpar concrete, you might not have structural damage like a ping, but you will have steel corrosion all over.
Right.
It'll look like your concrete is bleeding over the entire slab, despite the fact that we're paying money to make that concrete slab stronger and last longer.
Yeah, without a doubt. In the last century, when we used to use Brillo and it sat there on the sink in the little dish,
Do we just have some Brillo around here?
I'm still a fan of Brillo, but you're right, it gets,
and you could see that
Yep.
rust develop
yep.
Hey, can you,
a day
there's,
or two.
there's on the
Yeah.
middle
Oh, yeah.
bookcase, there's
Very
two
fluid.
jars. One of them has some brown liquid with a Brillo pad. I use a Brillo pad. You want to grab that for us? So, excuse me, sorry about that. You know, the threat of corrosion and the intensity of where it's at is real. There are plenty of measures and methods out there to enhance concrete, to make it stronger and last longer, to reduce, hey Steve, to reduce that impact of failure of concrete structures due to the corrosion of steel reinforcement, whether it's macro synthetic, glass fiber reinforced, using alternative binders, which we're going to be talking about later today, or using chemical admixtures like, Crete Shield.
Sure.
There's other means and methods, or just making a good standard or high performance concrete using basic materials.
Right. More robust, more durable.
And not throwing in water of convenience and blessing it.
Yeah.
There are
Well,
some.
because then you're just
Yeah.
opening up the surface for things to get in and have all kinds of.
So this was steel wool, and this started rusting after about 2 or 3 hours, and we put this in about 6 months ago. So the reaction is basically done. There's no steel wool left. This is one of our clients' admixtures. This is Crete Shield by Obex. It's one of their integral admixtures. And this steel wool has been in solution for 6 months
Yeah.
now. We put it the same day.
Yeah.
And this is another way of attacking that steel reinforcement using new and emerging, now enhanced admixtures to make that steel reinforcement last longer.
Absolutely.
Make that concrete stronger and denser and what have you. So that's it for today. If you have any questions, comments, or concerns, don't forget to like and subscribe.
I'm David.
I'm Whitney.
And I'm John. Go Concrete!
Beat
Beat
asphalt.
asphalt.